Right then. Thank you very much for coming along today. I know it's the last one of the day. It's been a long day. The weather's nice, and the party is next. So thank you very much. Big thanks to all the sponsors. Without them, this sort of thing is very difficult to put on. Gonna have a chat with them. Some really good stuff up there. This session, introduction to Amazon Redshift Cloud Data Warehouse. So before we get into that, who am I? I'm John Martin. I've been working with data for more time than I can care to remember, at least 15 odd years. Microsoft ecosystem, Oracle, AWS ecosystem, so most database engines, that type of thing, on-premises, cloud, you name it. That's enough about me. On to the important stuff. We're going to talk through essentially the cluster architecture. So what goes into making Amazon Redshift database service what it is? How does it function? Some of the capabilities and features that are there as part of the underlying architecture and how they work with each other. We'll talk about some of the way it stores data, because it's different to many other database engines, not only in the way that we need to model it, but the way that it physically stores it in the storage layer as well. Some of the database design concepts that dovetail with that in order to understand how to get the most out of it. Okay. We'll talk about some of the workload management features as well. There's control that you can have over it, but there's an awful lot of automated capability that you can turn on and use that will facilitate your workloads, making them more efficient, making them quicker. So we'll discuss those. And then we'll have a quick talk about some of the operational requirements around things like HADR, but also administrative tasks that you take on yourselves. Okay. That's what the session's going to be about. So where do we start? Let's start off with what is Redshift. Essentially, it's a database engine used for large-scale analytics. It's a relational database engine, so we're dealing with tables, views, the sort of tabular format. So if you're familiar with Oracle, SQL, Postgres, MySQL, those relational engines, fundamentally, that's what we're looking at, okay? Redshift itself is it started off as a variant or fork of Postgres back in the old version 8 days. Okay, and it's been evolved and adapted. So a lot of the language there, it's ANSI compliant SQL, but there's some Postgres elements to it as well. Okay, so when we're querying it, that's the sort of language we're using. But it's been re-engineered, the way that it integrates with additional services. So we start thinking about some of the elements of a large-scale data warehouse, whereas historically on premises, we'd be looking at loading all the data into the database engine. What we've got here is the ability to use the database engine and its optimized storage format and the ability to query the data, but we can also integrate with the data lake. So object-based storage, we've got Parquet, Avro, Awk, CSV, JSON data stored out there in the storage ecosystem. So when you start thinking about the modern data warehouse architecture, data lake house, Amazon Redshift can fit in to that as well and sit there above that repository and query it directly. So you can have some data in your database engine and some data down in the data lake and bring them together to give your users a unified view. There's the ability to reach out to other operational database engines as well. So if you're using Amazon RDS or you're using the Aurora services, either with a MySQL or Postgres engine, there's the ability to federate queries. So again, you can bring operational data sources into the mix as well. So really, it's a great way for giving you a high-performance window into what that data is. The analytics and the AI ML capabilities as well, there's some baked in so much as using SQL, you can create models, and it will infer a lot of the information around sort of, are we building an inference model? What are the parameters to use? Or you can specify them. That part of the SageMaker ecosystem, again, it's all brought in there so you can deal with it from the SQL side of things. And then there's gaining access to other external data sources. There is a data exchange within the AWS ecosystem in the cloud where you can consume third-party data sets, you can pay for them, but at the same time, you can publish your own data out to them as well if you want to monetize it and use it as a revenue stream. So there's a lot there. From a connectivity perspective, again, just coming in with our standard BI tools, ODBC, JDBC drivers, supports Postgres drivers. Okay, there is an optimized Redshift one for interacting with it. So that, again, if we want to use Power BI with it, for example, we can do that. If you want to use Tableau, if you want to use Click, all of those will interact with it. Same as if you're using your administrative tools, if you're using Workbench, if you're using Data Studio, things like that. If it talks to Postgres, most of the time it will talk to Redshift. Things like DataGrip or dbeaver, things like that, work fine with it. So that's where it sits. When you start thinking about some of the use cases that we commonly see for it, your traditional data warehousing, if you've got your on-premises, your big data warehouse, whether it's a pure sort of star schema, whether it's Snowflake, if you've gone for something like Data Vault as well, that can work in there. When it starts to get a bit more complex, if you're taking the sort of Oracle approach, potentially of having multiple layers with ODS, with sort of an Inman layer, where you're branching out to data marts and you've got that set up through schemas and what have you, it will work. Just takes a little bit more there. But those sort of traditional enterprise ones, a lot of people are migrating from their on-premises environment because it's not that scalable, or it can be, but for the right price. Whereas up there, it's a consumption-based model. You want more, you move the slider to the right, or you make the instance type bigger and you hit the button and it happens. And then you just pay the next bill that comes along, okay? As is the way with the cloud. We also see people building their own analytics applications over the top of it, software as a service, that type of thing, because there's not only the way to query it directly through the ODBC, JDBC drivers, but there's also a data API layer where you can actually pass inquiries and you can pull results back as well. Okay, and a lot of people start to integrate that ability to easily interact with large quantities of data to build applications and analytics software over the top of that to provide functionality and capabilities to their end users. And then finally, there's the big data analytics piece where it starts to really bring in that data lake. It starts to bring in the AI and ML capabilities that exist, where you're bringing in more services. Because when we start thinking about what a modern data warehouse is, it's not just a database. It's a collection of services that we're using to deliver capability to our end users. So those are the three sort of key, I say, use cases, buckets that I see a lot of customers using the platform for. And a lot of them will start off with just a simple, right, I want to move my database engine up, and then I will diversify it out. I will start bringing in the data lake because I want to leverage the ability to use Spark for my ETL layer. So I've got people landing data into S3, for example, and then I'm using Spark to validate it, to manipulate it, to enrich it, move it more towards the curated high performance layer where I've got that defined insight that I'm delivering. Okay. So, any questions so far? Feel free to ask questions at any point. I'll also be around at the end of the day if you want to think of anything after. Okay. So, that's been a high level view. What does it look like under the covers though? So, your typical Redshift environment at its core is the Redshift cluster. Okay, referred to as a cluster because we have multiple components here. We've got the leader node and we've got the compute layer. Okay, there is one leader node. Kind of name gives it away. This is what we interact with. Okay, we've got a common endpoint as well, which we point our tools at, whether it's an administrative tool like Workbench or whether it's a analytics tool like Tableau. Okay, the leader node will take your query. It will basically optimize it. It will build a query plan. It will compile it down into C++, and then it will distribute that to the compute nodes, which then do the work. Okay. The compute nodes are the bits that interact with the storage layer. Now, what I'm talking about here is what's referred to as the RA3 family of instance type with Redshift. There are two instance families that we currently support. DC is the other one, and we'll talk about that later on, but RA3 is the latest generation where there's a lot more features coming in because we've separated compute and storage. They scale independently, okay? So if you've got a large amount of storage and you don't need much compute, RA3 is great because I'll have 4 compute nodes and I will have hundreds of terabytes of storage. Or I need a lot of compute but not much storage, then you can flip that around. I'll just have those and you don't have to use it. You don't pay if you're not using that storage, okay? The Redshift managed storage is where we actually store our database files, if you will, the files that go into it. Now, the files themselves are 1 megabyte immutable blocks. So when I load data, it gets written into a 1 megabyte block. We end up with many of them, okay? We access them in parallel. That's how we get the high I/O throughput. We'll go into it in more depth about how it does that data access later in the session. So that's the fundamental core of it. Now, integration with the data lake. We can There's additional services. There's one called Glue Data Catalog. Essentially, you can create a crawler. It will crawl an S3 bucket, and then it will present that information back in a way that you can then ingest through the metadata layer. So it describes the files as a table. Okay, that's where I can use CTAS to bring data in. Alternatively, I can define my schema and I can use the copy command. The copy command will then ingest the data from Parquet, from CSV, from Avro, from Awk, from JSON, whatever. Okay, it will bring it in. I can bring all the files in a folder structure. I can bring in some of the files by specifying a manifest. Conversely, I can also unload to S3 as well. So if you're using the Redshift engine as part of your ETL pipeline, bring the data in, do some processing, stick it back out to the storage layer. Okay, or if you want to age data out and it's not already there, again, unload. You can get it to create those files. Now, the way you structure that is obviously the way that the compute nodes are set up. They're also broken down, and we'll talk about the slices in a moment. But essentially, you want a number of files that is divisible by the number of slices, and they should all be of an equal size, because that way you get balanced processing, and we get that parallelism. Now, behind the scenes, rather than the compute nodes doing that work, there's what we refer to as the Spectrum engine. This is essentially a pile of background compute that, when needed, the cluster will call upon based around the amount of data, the number of nodes you've got in your compute cluster and things like that, and basically say, right, I need this many Spectrum nodes, and it will offload that, and it will push that heavy processing down there. So if you're querying the data lake in an ad hoc manner, okay, you can actually get a lot of capability pushed down into the Spectrum layer and offloaded from the compute nodes. So they can keep doing other things and continue with other bits of workload, and then Spectrum will give that back. Certain query types where you can't get that pushed down, thinking about distincts and so on and so forth, where obviously that's going to need to go up to things like the leader node before it can take that information and pass it back to you. The compute layer and the leader node both have caching elements, so a raw data cache essentially there in the compute nodes, so it will lift data out of Redshift managed storage, store it there. There's also a results cache up on the leader node as well, so if you're issuing the same queries again and again, you're getting them from cache necessarily before going down to the underlying storage layers. We've got the federated query, which I spoke about before. Again, if you're using Amazon RDS or Aurora with Postgres or MySQL, again, you can just create them as external data sources and query them to bring that data together. So it's very easy to give you data from the Redshift managed storage engine, from the data lake, and from an operational database source, all in one query, bring that together and give that back to your user. Other integrations. So we've got the data exchange that I just spoke about. That's tightly integrated, so you can ingest and push data out as needed. SageMaker is the machine learning element. Okay, there is functionality there to, like I say, create models and such like from SQL, and then also be able to call them as part of a query so you can get inference information and what have you. Alternatively, you've got the SageMaker sort of service ecosystem as well, which can be used to query and work with Redshift. So if you're using things like Jupyter Notebooks, that sort of thing, all of that works in there. The other one that's really powerful is the ability to use AWS Lambda. So Lambda is essentially, who is familiar with the AWS ecosystem? Okay, it's the right crowd. How many people are familiar with the Microsoft Azure ecosystem? Okay, Lambda essentially is a serverless compute platform where you can deploy code and it will run. Okay, so I can build functions within Redshift that use either SQL or Python. If I want to do processing with C# or Java or Go, I can write that code, deploy it as a Lambda in that serverless compute engine, and then I can call it and essentially reference it as an internal function in my SQL code. So it will pass that data out to Lambda, it will do the processing, and it will get the data back. But again, you just define it as a function, and it's a function call within your select statement or whatever, okay? So we get that functionality. So it's really good for doing third-party extensions, so things like tokenization. So you want to store obfuscated data in the database, but have the real value held somewhere else. There's various third-party solutions out there that have that type of integration. Very, very powerful, especially for things like PCI DSS compliance, or you want to secure PII data, things like that. The database, it's not like dynamic data masking where the data's there. It's actually completely obfuscated. You've got a token which has got to go off to an external service to do that lookup for you. So you're essentially passing that risk off. Okay. It also has the ability to auto scale. Now, this is a feature called concurrency scaling, which you can enable. So if you get a spiky workload, if it's you get, say, a 30-minute sudden big spike of activity that comes in, lots of queries. If you've got concurrency scaling enabled, the Redshift cluster will actually spin up additional Redshift clusters in the background, offload the workload, and then pass it back. So essentially, it's still coming through the primary endpoint. You don't see these clusters. And for the first hour of the usage for that feature, you're not billed for that extra compute either. So essentially, you get an hour's worth of burst compute a day for free. Then it's billed per second after that. What that gives you is, as your workload evolves over time, it's really useful, it scales out, you can monitor it, and then you can start saying, actually, I need to schedule an elastic resize so that ahead of this, it's going to go, or I'm going to modify those queries, I'm going to improve them, I'm going to look at my workload. But it gives you that extra buffer and safety net, okay? But very, very useful. There is also a serverless version of Redshift in preview at the moment, which is basically you set how much you want it to allow it to use, and then it will fire up as and when the workload comes in. So that kind of gives you that functionality, but as a core element of the platform, it automatically scales. And then finally is data sharing. Okay, so if I've got multiple Redshift clusters within my organization, one for finance, one for sales, one for R&D, for example, okay, and I want to share data between them. Do I want to publish data and replicate it? No, because that's data movement, and that's not great. And obviously, if I'm the finance department, I'm owning that data, I don't want copies of it necessarily winging around, maybe being out of date, things like that. Data sharing essentially allows you to publish the visibility of those database objects, views, and tables. And when the consumer cluster is granted access, says, okay, I want to consume that, creates it as a database, an external sort of schema. When I query that, I'm actually querying the Redshift managed storage that sits underneath the other cluster, okay? So it's very good for sharing data between organizational departments, but it's also very useful for breaking out and taking this sort of one cluster to rule them all type model and breaking that down into saying, actually, I've got a cluster that's specifically set from a compute perspective to handle my BI tool workload, okay? It's still querying that underlying data, but it's different compute from the main cluster. That main cluster doesn't have to be online, so you could be using that purely for ETL ingestion, another cluster here for servicing your BI tooling. It's accessing that data. I could have a serverless cluster configured up here that's referencing that for my analysts who are performing ad hoc queries, for example. So using that data sharing functionality, it just allows you to give that window into the underlying storage without it being replicated, one instance of storage, optimizing costs and performance. And as soon as that data is ready in that underlying storage layer, it's visible to all of the data consumers that have been configured for it. So that's a high-level look at what the cluster is and how the service hangs together. And these are all the capabilities and features that allow us to build analytics platforms that meet the requirements and the SLAs that our users have for getting their reports in a timely way. Now, one last thing to cover is the way that the compute nodes themselves are broken down. So there's what's termed an instance type, okay? So for RA3, that's XL plus, 4XL, XL, 4XL, and 16XL. Okay, we'll have a look in a minute. But essentially, it takes that compute and subdivides it down into further sort of partitions, if you will, for compute, memory, and storage. This is where we end up with that massively parallel processing, the MPP capability, which underpins the Redshift performance. What it does is it distributes data across all of these slices, or can do, if that's what we configure in our data model, so that when we access it, we access all of that in parallel. So I'm not waiting for one huge table scan. I've got N number of scans going on at that piece of time, doing some processing, doing some joins, that type of thing, and then feeding all of that back. Okay, so that's how we get it. So the RA3 family, like I say, that's the spec of the instance type. So X large has got four vCPUs, 32 gigs of RAM, and can have 32 terabytes of Redshift managed storage per node. Okay, so you take that and multiply it by however many nodes you've got, and that will give you your storage and separation compute. And it's got two slices, so that 4 and 32 is subdivided into 2 CPU cores and 16 gigs of RAM per compute node per slice. for 4x large, 12 CPUs, 96 gigs of RAM gets broken down 4 times, but the RMS, the Redshift managed storage, gives us up to 128 terabytes of storage per compute node. Okay, and 16 if you've got a really big workload, 48 CPUs broken down again into 16 slices. The other family I touched on briefly earlier is DC2. This is known as dense compute, where there's a bias to compute capability over the amount of storage that we have. So there's the DC2 X large and 8X large. So again, there you can have up to 32 CPUs with 240 gigs of RAM and 2.5 terabytes of NVMe local. Okay, so these ones are close coupled storage and compute, but it's broken down to 16 slices. So again, depending on what your workload is, there's an option for it there. Okay, and it's easy to sort of migrate between them if you have to. So that's how the cluster looks. That's how it's broken down from a compute and memory and storage perspective. Then we start thinking about the storage itself. Now, who's familiar with SQL Server, Postgres, Oracle, things like that? Okay. The way that they store data is essentially what I'll term row-wise, typically. Okay, row store. So I've got a data page or data block that's being allocated, and it contains all the values for a column. And there'll be multiple rows for those given the size of the data page, depending on the amount of data that's getting loaded in there. When I query it, I've got to pull the whole page back. If I want 2 columns, I've still got to read all of that data. Okay. When you start thinking about OLTP platforms, that makes a lot of sense. I'm dealing with records a lot of the time. When you move that to an analytics workload, and I'm dealing with large volumes of data, typically with a subset of rows, I want to run a sum, I want to count, I want an average, things like that. Row-wise row store doesn't necessarily make sense, and this is where column-based storage comes in. So the engine for Redshift is columnar in nature, only columnar. There is no mix of row-based and column-based, okay? Row-based for everything. Which means that in a data block, I mentioned earlier that 1 megabyte immutable block of data means that it's got a whole pile of row of values related to that column for n number of rows. Depending on the data type size you've got, depends on how many you'll get in there. That columnar storage then allows for effective compression of the data. So again, it's compressing a lot more data into those 1 megabyte blocks, storing them efficiently in a distributed storage platform, accessed in a parallel way, and distributed across multiple compute nodes. So again, we get that parallelism, which helps us be able to run those queries effectively. Okay, if we got good levels of compression because lots of repeating values, again, that's going to optimize our storage costs. And when we get to the cloud, everything's transactional in nature when it comes to how much we're paying for what we're doing. So again, optimizing the way we run compute and optimizing the way we do storage is very, very important, irrespective of the cloud platform that you're using. So, as I said, when it comes down to the column size, the column storage mechanism, if I've got a example table here on the left as you're looking at it, if I want a particular column, so I want the minimum DT from that table, if it's row-based, I need to go through and read all of those columns. Where in the column storage, essentially, the engine knows that actually I don't need to bother with any of those data blocks for anything that's not associated with this column. So again, you're optimizing I/O by not doing any. If you're not doing it, it's not going to take time. You're not going to burn compute, okay? So that's really where the way the columnar engine works. So we specify it. So again, don't go select star, that type of thing, okay? Because that's not going to help. Be very focused in what you're doing. The database itself and the design that we then take from that, in that we've got these column-based 1 megabyte chunks, okay? We start thinking about the way we're going to design the database, the data model itself, okay? First thing to understand is that it's fully ACID compliant, okay? ANSI SQL. It uses a serializable isolation model, and it relies on parallelism to essentially give us that throughput. Okay, if we've got a balanced distribution of data across that parallel processing, then it's going to perform very well. If we end up with skewed data, then less well. Okay, and we manage that through what's referred to as distribution keys and distribution types and sort keys. Okay, now when we start thinking about the Redshift engine itself, we define the table, and we can define the distribution keys and the sort keys, and that will have a bearing on how we manage that data. Okay. That's how we optimize the I/O about what it's going to be doing. We give the engine a lot more information about what that data is. When we ask it those questions and the queries we're asking, that's how it will optimize the data access layer, okay? One database by default uses schemas, but you can, I think it's up to 100 databases. But typically you're not going to be doing that because you've got the schemas and everything like that. Database models themselves really depends on what your workload is. You can achieve good performance with most modeling techniques, data vaults, star schemas, snowflake schemas, things like that. Full sort of third normal form OLTP style databases, there's a lot more that you need to do there, but it can be done, not advisable. The most appropriate is star schema, given the way that we're working and the types of queries we're doing. We're minimizing our joins, minimize the complexity that we have to build into our data model with regards to how we're going to be either co-locating or distributing data, okay? So it is very, very important to understand the data model and the way we're going to work with it and we're going to query it. It's going to have a bearing on how we distribute or co-locate data to make sure that that's doing it effectively. Because if you think you've got data on compute node 1 that joins to data on compute node 4, we've got to make a decision about how we're going to shuffle data around. We're going to copy it which way, okay? That is going to add increased latency into our overall processing because we've got to move data around. The laws of physics dictate that if I'm moving things across a wire, it's going to take a bit of time versus it being locally, okay? So, bearing that in mind, if we go for a start schema, okay, and we define our tables, we've got the choice. When it comes to the distribution of data, okay, the distribution types, okay, auto, let Redshift figure it out, okay? So, this is the default. You create a table, you don't specify distribution style, you don't specify distribution key, okay? Based around your workload, Redshift will basically do some analysis, it will run it through some machine learning models, and basically say, okay, given the way that you're querying this data, the best way is for me to service your queries in a timely way is to use this distribution key and this distribution style. It will then implement that for you, okay? If you've got a new workload you're taking, it's a great place to start. If, however, you've got a very well-known workload, you can set them yourselves. So you can say key, all, or even distribution styles, depending on the workload, depending on what the data is, depends on what your workload is. If you know what that can be to optimize it, you can go there yourselves. You can set that up, okay? But if you set auto, as your workload and data evolves over time, you keep feeding it through those models, it will update that and it will change it. So it can take that workload off you, okay, from an administrative development standpoint. So just bear that one in mind. But again, if you've got a static workload that's well known, you can optimize that yourself, okay? So what do these look like? If we go to our deep dive table, okay, we've got airport ID, location, and date. We've got the three different types of distribution style, the functional types of distribution style there. Okay, so if we add a row, okay, for San Francisco, for the key distribution, it's not showing up well here, but essentially the key the distribution key that's been picked is the location. Okay, so if we insert that, what we end up with here is on slice 0 and even, we've got a record. The key has taken SFO, hashed it, said, right, it's going to go here. And then in all, it goes into the leading slice on each compute node, okay? We add another record, this time for JFK. Goes into slice 1 on node 1. So it's essentially going to do a round robin. For every row that comes in, I'm going to put it here. The JFK value hashes to something different, so it's going to go into slice 2 on the other node. And then for all, it just goes on the bottom on the leading slice. We add another SFO, gets added in the key one to the bottom of the existing one. On even, it just goes into the next available slice. We add another JFK. You can see there we end up with them on the leading slices on each of our nodes in that instance because of the way that they've hashed together. Even has spread it out evenly across all of them, and all has put them in the leading slice on every compute node. So again, thinking about what we're going to be doing, is there going to be a case of, well, all of my fact tables join to date, for example. Okay, well, maybe I want to put date on every single compute node to minimize that data shuffling, because I've got a point where I'm doing some restrictions and things like that on it. Okay, I'm doing those joins all the time, so I want that present on all of my compute nodes. There's certain cases where if you've got very large fact tables and potentially a very large customer table you're commonly joining on, then again, potentially if you do a distribution key for customer ID on the fact and the large customer dimension table, the data will collocate. But essentially what we want to make sure is that we end up with a very high sort of number of values within that column so that we don't end up with data skew necessarily causing us a problem. That's something to just be aware of. If you have got data skew in that column, then when you run that query with that particular value, it's going to end up taking longer on certain areas, which means our overall compute time is going to run up. Okay. So that's how we end up with the parallelism. How do we optimize I/O? This is where our sort keys come in. Now, there is the ability to get Redshift to automatically pick the sort key based around the workload. Okay. Much the same as you do the dist style, dist key. There's two different types, there's interleaved and compound. Compound essentially is like our traditional sort of row store indexes of column, 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 and it will say I'm going to order by the combination accordingly. And the interleaved essentially is I will take this column and sort it, and then I'll take the values from this column and sort those and put them together. Okay. Don't see too many people using interleaved very heavily. Typically it's compound. A lot of the time it's just a single column for sorting. Now, what this means is, for things like when we're doing join predicates, we want distribution keys or distribution elements potentially being part of that. We do not want a distribution key in our where clause. We want a sort key in our where clause. Okay? By putting the sort key into the where clause, that's what's going to tell the engine that's what I'm interested in, be it a range of values or discrete sort of equality predicate. That's how it will do the restriction on the data blocks that it's going to go and get. So if we go back to our table and say, okay, here's deep dive, where give me all the records and give me a count of all the records where it's the, and this is an American date, so 9th of June, 2017. If I've got an unsorted table, I've got 4 blocks of data, and you can see there that it's not been sorted by date, okay? If I actually sort it by date, then when I run that query, on the unsorted table, I may be accessing 3 blocks. On the sorted table, because all those values sit within the min and the max for that data block, then the engine knows I just accessed that one. So it's a third of the I/O. These are what's referred to as zone maps. Essentially, they get the engine will track the min and the max value for every data block because it's one column's worth of data. You get the min value and the max value. That's how it will be able to do that restriction. And again, it will minimize the amount of I/O that it's doing by eliminating the need to go and look at those other blocks. So again, come down and picking effective sort keys based around what our predicates are in our where clause is what can give us that improvement in performance because we're not going to do the I/O. Okay. Where are we? Okay, we're on time. Workload management. This is the next thing. Oh, one last thing to quickly touch on around the auto element of it, for the auto tuning, for the tables, the auto table optimization, for distribution keys and sorting. It relies on the object ID, okay? So if you have an ETL pattern, which essentially involves you dropping the table, recreating it with the same name but new data, that will nullify the ability of the system to be able to automatically tune it effectively. Okay, because that ID is not consistent. It doesn't look at the name, it looks at the internal ID value when it's doing those calculations. Okay, so just bear that one in mind. Think about what's going to be the most effective way to do your ETL. If that's what you're currently doing, you're not going to be able to leverage that auto table optimization. Okay. Anyway, moving on, workload management. Again, there's a lot of functionalities here that are built in by default, and it's on by default. So automatic workload management. You get up to 8 queues, which allow you to prioritize workload accordingly, based around a number of parameters that come through. But essentially, it's there to give us improved concurrency. So we don't end up with one behemoth query coming in and blocking lots of small ones. Okay? Essentially, we end up with that big query sitting in a big query queue, and the query, small ones running through another small query queue, we can see how much resource they're using, and so on and so forth. So again, it can categorize that workload, put them in the queues themselves. Really, really good if you've got an erratic, unknown workload where you've got people issuing ad hoc queries, they've got running reports through the course of the day with varying different parameter sort of settings. So you end up with someone running a big query 1 minute, a small query the next, but you don't know it. You can manually configure those queues yourselves, okay? That can be done, again, if you know your workload really well and it's not got a huge amount of variance in it, that can be very, very useful. You can optimize it yourself. If it's not evolving over time, that's great, okay? Building on top of that, we've got query monitoring rules. And this essentially looks at several things like compute time, data scanned, the duration, things like that. You get the option to essentially say, do I want to log this information? Do I want to abort the query? Or do I want to hop over and just let it carry on, okay? My general recommendation is for query monitoring rules, always set what you define to be a threshold for amount of compute time, duration, data blocks being scanned, things like that, and log it, okay? Log that data. It's useful to have, because if someone comes to you, as they always do, the next day, my query ran slowly yesterday. Well, what query did you run? Then you've got to set up monitoring. You've got to say, oh, capture it, run it again, let's see if it happens, okay? Whereas obviously if you've got that information to hand, you can go back through the logs, you can say, okay, that's the query, drill in, look at the explain plan, understand, okay, well, why did it go wrong? Why did it take long? Why did it breach this? Did they just pick, I want to look at 25 years worth of data? Well, really? Do you want to be doing that? Is there not a more efficient way that we can do this? Okay, you do need that, fine, then we can move forwards with that sort of thing, okay? You can create up to 25 rules across all of those 8 queues, okay? It's also a sort of guardrail against those big runaway queries, okay? So very, very important. If you're someone who is trying to scan everything, do you really want to allow that to consume those resources within the cluster? You can set those guardrails up to abort those queries, okay? So it is very, very powerful. There's also a feature in there called automatic query rewrite, okay? So this is a mechanism whereby, because when we create the tables in Redshift, we don't have the concept of what are termed secondary indexes. So if you've got your clustered index and your non-clustered index in traditional terms, you've got the table with the data in Redshift. It is distributed as it is, and it is sorted as it is. If, however, you've got a small portion of your workload that needs to query that data in a slightly different way, needs a different sort key, for example, or needs a different distribution style, then materialized views can help, okay? Likewise, if you're doing large aggregates, you're doing sum, you're doing average, you're doing whatever, okay? If you create a materialized view, it will materialize that result set. Auto query rewrite will take your query, and because it knows about what's in those materialized views, it will say, actually, I'm not going to bother running that aggregate against the base tables because I know you've got it done over there in that MV. So what it does is say, I'm not going to bother dealing with that table, I'm going to talk to that materialized view because I know I can service the query more efficiently. So again, it's looking at that from an optimizer perspective. So materialized views in your traditional sense can take the place of secondary indexes to serve specific queries sort of within a subset of the workload. So bear that one in mind. There is also a feature in preview right now, which is called AutoMV, Auto Materialized View. This is based, again, around analyzing the workload. If the engine thinks that if I create a materialized view with this definition, it will allow me to improve the workload performance, it will do it, okay? So you can say, turn the feature on, create them, it will do it in the background, you won't have visibility of them, it will create them based around the workload, and then as the workload potentially changes, it will get rid of them as well. Okay, so again, it's got that ability to start tuning the way that it's optimizing the way that accesses that underlying data by materializing result sets to give you that performance improvement. Okay. From an operational standpoint, once we take it into production, how do we make sure the optimizer is giving us good query plans? It's executing queries effectively. This comes down to table statistics, okay? Number of rows, the amount of data, potentially some data skew, okay? You know what I said earlier about if it's got data in different compute nodes, it's going to figure out, okay, which way do I need to sort of send data around? Do I need to distribute to everything? Do I just move it to one place? What do I need to do? Okay, that's effectively handled through the table statistics. Now, when you're loading data, they're automatically calculated. Okay, it's great. Table statistics, they're there, they're system properties. The query optimizer looks them up. Now, obviously, if you're doing lots of small changes over time, then that distribution can change, what have you. Now, during periods of low activity, Redshift will run a sort of a table analyze, essentially, looking to update those statistics on an hourly basis. If the workload is very sort of low and there's plenty of capacity there, it will run that activity for you to keep them up to date. However, if your workload is constantly at a high level, then you need to take that burden on yourself and schedule them at an appropriate time. So again, just think about what you're doing there. If the auto functionality is not being able to keep up with keep the table statistics fresh, when are you going to run them? Set up scheduled queries, use something like managed airflow to coordinate it. There's various different options there, but you'll need to take that burden on yourself, okay? Likewise, when it comes to table management and reclaiming space, I said those 1 megabyte blocks are immutable. So when I run a delete, it doesn't delete the data, okay? It just essentially marks the record as delete. The block is still there, just gets skipped when you start coming back to query it. Updates are a delete and an insert on the end, okay? Now what that means is, when we're doing our ETL, if you've got type 2 SCDs or so on and so forth, and you're doing updates or you're purging some data out with a delete, things like that, you're going to end up with essentially a lot of wasted space in those 1 megabyte blocks. So what we need to do is run a vacuum. Now, again, during periods of low activity on an hourly basis, Redshift will run vacuums. Great, it takes that work burden off us. But again, if we're running a consistently high workload, maybe we want to start thinking about building a vacuum into the end of our ETL process, okay? Because what it does then is it will basically move all the good data to new blocks and discard the old ones. So what it means then is you're actually optimizing the amount of I/O you're going to be doing because the data those blocks are full of useful data and there's less of them, okay? We'll have a look at that in a demo in a bit. The vacuum as well will also look at resorting. So again, if you're ending up with data that's out of sort, you end up with a lot of data in different blocks. By running the vacuum, it will resort them. If the data is actually already sorted beyond 95%, then it will skip the sorting element and just do the vacuuming. Okay. And then finally, the monitoring piece. This is really, really important to any operational platform. You need to understand what's the behavior. Okay, what does normal look like? Because when things start getting abnormal, you need to be able to go back and say, how does this variance deviate from my baseline? If you have not got a baseline, and you don't know what normal is, it makes troubleshooting a lot more complex. Okay, you want to do query optimization. What is normal? Once you understand what normal is, it makes our lives a lot easier. Now, you've got CloudWatch, which is a mechanism for, it's another part of the AWS ecosystem, which is about monitoring. Okay, what that allows you to do is bring together metrics and logs from multiple different services to give you a single dashboard, which is one picture of the truth for the whole service. So if you can bring in storage, networking, Redshift, so on and so forth, okay? So you've got all of that information to hand. There's also a Grafana managed dashboard. So there's a managed Grafana service available, or if you're using the open source one, there is a dashboard which you can use with some additional queries to get some deeper insight out of what's going on in the Redshift engine itself, okay? So again, you get that visibility, you get that history, really, really important. There's also in the console, the Redshift Advisor. Now this is one where it will give you sorted tables, non-optimal sort keys, distribution keys, styles, things like that. If you're doing data loads using copy, and for example, it thinks that if you would compress the source files, you get better performance, you'll get those sorts of recommendations through the advisor. So again, you've got that insight coming back to you. So it's well worth having a look at that. But if you go to production, you haven't got proper monitoring, it's going to make your life difficult. Even though it is a largely managed service, having that monitoring in place to give you that insight is invaluable information, my experience. Cool. So what we'll do is we'll touch now briefly on the HADR piece before we go into some demos. The backups for Redshift are snapshots, okay? Now, snapshots are taken automatically, and every 8 hours or 5 gigabytes of data change, whichever's first. So again, depending on what's going on, it's looking to minimize that potential sort of RPO. So if you have got to restore from a snapshot, woe betide, you can replicate them off to another region. Okay, so normally they're stored down in S3, which is, so in AWS, we've got the concept of a region, which is a geographic location. Within that region, we have what we term AZs, availability zones. Okay, the availability zone itself is then comprised of 1 or more data centers. Each region has minimum of 3 AZs. Okay, S3 spans all of that. Okay, so when the data gets copied down, the resiliency there is built in. Okay, so if there's a problem with an AZ and you need to restore the database, restore the snapshot, you can do so easy enough. We'll talk about AZ resiliency for the compute layer in a moment. I can ship it out to another region. So if you've got a requirement for regulatory requirement or business requirement that says, I need to have off-site backups, then you can configure it to ship that snapshot to another location. You configure the duration for retention anywhere between anything up to really 35 days. Okay, so it's really geared towards that operational element. When it comes to doing the restores, you can restore one table into the existing database, multiple tables into an existing database, or you can take the entire snapshot and restore it to another cluster. You can also restore individual tables to other clusters as well. Okay. There are also manual snapshots, and this is where if you've got a long-term retention requirement, you can either convert automated or you can have a scheduled job that's kicking off manual snapshots. Okay, again, stored in S3, can be replicated to another region. You will, however, unlike automated ones, incur additional storage charges outside of your Redshift charge for manual snapshots, okay? Because they're controlled by yourself. They're not part and parcel of the service, okay? So just bear that one on. But if you have got a long-term retention requirement, that's the route to go down. Multi-AZ resilience. Now, obviously, outages happen. Very, very, very rare to happen at region levels, okay? More often than not will happen at an AZ level in using AWS terminology. What this does is when you create a cluster, when you deploy it into what's termed a VPC, which is a virtual private cloud, where you define the networking, okay? You define multiple subnets. You create what's termed a subnet group, which brings 2 or more of those subnets together, and they have to be in different AZs, which means when you deploy a Redshift cluster, you're deploying it against the subnet group for its networking, okay? So what it means is it will put the compute in any of the available AZs associated to where the active essential subnet is for that cluster. If there's a region outage, boom, flips, brings it online on the other side, okay? Because that Redshift managed storage is sort of spanned across at the region level again, you've got that level of resiliency there, that separation of compute and storage. Okay. You can also trigger a manual failover between AZs yourself. Just go into the console and say, relocate my cluster. Boom. Okay. Nice and easy. There is also the ability to resize or pause the clusters, depending on what you're doing. For example, if they're development non-production clusters and you want them off at the weekends, things like that, one of the things I've found is to use a scheduling tool of your choice. Use a tagging using a tagging regime for the cluster resources and say, turn it off at the weekends, and have essentially a job going through parsing the resources, pulling them in, looking at the tags. Do I want to turn this off? Pausing it. That way you don't get paid for the compute. You don't pay for the compute. You only pay for the storage you're using. Then you can have another task that essentially turns it back on Monday morning before the developers come in. That type of thing. Okay, so you've got that ability. Elastic resize. I want to change the node size or the number of them, and I can do that with minimal disruption, versus a classic resize, which essentially is give me a new cluster and move the data. That one takes a long time, a lot more disruptive. Okay, so that's been a quick look at Redshift. It's been a quick look through the capabilities and the cluster. What we'll do now is we'll quickly jump in. I'll just sort of going to do a demo of basically loading some data in, querying it, and having a quick look, just to illustrate some of the points there. But before I do that, has anyone got any questions? Yes.
How Redshifts go for example, updating a large volume data? Because we keep some snapshots of our tables, and then we have historical migration. Like, we need to do some special tricks, or is it as fast as inserting the data?
So let me just check I've got the question right. So how would you do a very large-scale data update in Redshift to a fact table?
Yeah, for example, is it like this, or I know I'm looking at more like a relational, or
Yeah.
some partitions values,
So there's no partitioning because it's distributed data across. It's going to depend on the volume of data and the type of update you do. But essentially what it will do, because it uses serializable, it will, any queries coming in will be able to see the old data until it's complete. How long that takes is going to be entirely dependent on the work you're doing there. There are options around potentially using a view layer, swapping views in and out, that type of thing. Multiple tables in there, that type of thing. It gets a lot more complex. There's no concept of partition switching or anything like that. It is a case of dealing with that base table. So it's entirely variable about the update. Depends on how big your cluster is and everything like that, because again, if it's one column and it's discrete data types and it's not that many data blocks, it's pretty quick. Okay. So yeah, so if you wanted to update one column, a terabyte's worth of data in a small period of time, if you're going through it, if it's distributed over a cluster, again, and it's a lot of compute there, it will just run through it as quickly as it can. But there's no need to look at sort of handling things like redo logs that you would in Oracle about whether you're going to do that. The other option, again, is pull it out to a temporary table, update everything, move them. Yeah. So there's various different options. Cool. Right. Demo time quickly. Oh, yes.
So, just curious, because you said if you do it with serializable, the readers will see the old data until this update is completed.
Yeah.
So it is using some sort of snapshot.
Essentially, yeah, in the background. Can I demo it? Let me see if I can do a demo at the end if we've got time, Erlen.
Yeah,
I'll show.
Yeah.
There it is. A second just to switch it to screen mirroring. And jump into the console. Quickly look at the Redshift console. Bear me a second, I'll zoom in as we get to the important bits. So this is our cluster dashboard. So this is where I can see information about the clusters. I've got 2 of them there. They're on. I've got 6 snapshots there. If I then come across and say, actually, I want to jump into this cluster, this is where I get more information about what its name is, cluster namespace is, node type, number of nodes, connectivity endpoints, all that sort of stuff. Down here is where I get more of the properties. So I can see parameter groups, database name, port numbers, things like that. Performance metrics, again, I've got the dashboard here. Oop. Oh, no, I've just gone back. This is where, again, I can just look at my cluster performance. This is where I've got the recommendations for advisor, any alarms. This is where I can see my CPU utilization, storage space used, that type of thing. So I've got something here in the console, but CloudWatch gives you that ability to build a unified dashboard view over everything. So what I'm going to do is quickly connect to my database. Not that one. I want that one. Okay. 5 minutes, perfect. So what I've got here is we're going to copy some data in. Okay, so I'm using a TPC data set. So I'm going to create a table, distribute it on the order key, and I'm going to sort it by order date. Okay, so again, when you think how that's going to be spread out, I've got a large number of values in the order key, so it's going to spread out quite well, nice and evenly, hopefully. I'm going to use the sort key for order date because that's what I'm going to be essentially restricting it on. So we run that. Give this a moment to wake up. There we go. So now what I'm going to do is I'm going to copy some data in from S3. So I've got the copy to orders. So orders is the table from this S3 file, or as a folder structure. The IAM role, so essentially the way that I control access to the S3 buckets and other resources is through what's referred to as an IAM role. So this defines, in conjunction with the policy, what I'm permitted to access, and I associate that role with a service. So I've got fine-grained control over what it can and cannot access, okay? And have multiple IAM roles, again, so you can decouple it and compartmentalize everything there. And it's going to be pulling the data from the US West region 2. It's LZOP compressed file. The delimiter in the file is pipe, and it will set all of the updates for the statistics and everything like that as it goes through. So we run that one. Should take about 40 seconds to complete and load about 76 million rows on a 2-node cluster. Okay, so he says that. 40 seconds. Any questions about anything so far? Okay. So what we're going to do once that's loaded is we're going to start looking at the number of blocks associated, spread across the various different slices for us here. And what we'll do is then we'll go in and we're going to run some deletes, and then we'll see, okay, well, just running the delete doesn't claim the space. We've got to actually run the analyze. If I left it for a little while and it ticked over the hour and auto vacuum kicks in, then that makes life a little bit easier for us. Ooh. Yep, 43 seconds, 76 million rows loaded. Efficient. So, if I come down and run this one, and then we'll look at the result set. The reason you'll see it is most of the queries are taking about 7 seconds or so is the way that this query took. There's a new version of the tool, which I've not got this count set up for, but this one's using the data API to store everything essentially in S3 and then present it back to me, but it's also the compile time. But anyway, as you can see here, I've got the first column essentially is the number of slices set up, and I've got the number of blocks per element there. So if I come in and delete a stack of data, so let's run that. Here we go. Wakey wakey. Nice and easy, 7 seconds. So that one's run. We deleted some of the data. So let's go and check what it says. We'll lead with the first one. Should still be up about 256. Yes, 256, 248, 24. Let's make that a little bit narrower so it brings it across. So what I'll quickly do is also just open. Come on, thank you. Another query window. Come back down to here. Got 1 minute left. We'll grab these two. We'll run a vacuum delete. So that will do the reclaim of the space. Run that, and then we'll just check the block count. That's just running through for us. Shouldn't take too long. Run. 15 seconds. Then if we run this one, again looking at the block lists there, we'll see now, there we go. Our counts are dropped, so the first one was 256, then it's 248 on the last query. Here we're looking at, again, the number of blocks that are in use because we deleted that data, it's been consolidated. So again, that's an important thing to make sure that happens. There is also, if I run a copy command as an issue, so this one will fail. There is also the ability to go and look at information in the system table, system views, which will tell us why. So that one barfed, which is what we expected. We run that query against a a view I've created where I'm looking for the customer table. So if I do end up with a failure, I can come in and have a look and actually find out, scroll across, that for CNation key, there was an invalid digit value of H when it should be a type of long. So again, I can get that information about why loads are failing. So that's been a quick look at just something to do with Redshift. Let me just find the slide deck again, and we will quickly do the summary, and we should be good. Get rid of this. I don't know why that's still there. Come here, thank you. So last one there. It's a managed data warehouse, managed database service, lots of auto capabilities in there for tuning, table optimization, things like that. Lots of integration with other associated services for a modern analytics platform as well, which you can integrate and use over time. It's a massively parallel processing engine. So again, think about distribution of data, sorting it effectively, managing that I/O at scale. And again, those workload management capabilities will help us aid concurrency, service the workload we have for our users, and really sort of deliver the analytics capabilities we need at the scale that we're going to be working with many, many terabytes worth of data now without having to go and spend lots of money on hardware. So with that, thank you very much. Don't forget the party is next door. But first the picture. Oh, and then there's a party. So thank you very much for your time. Really appreciate it. Hope you have a great rest of the conference.